In this video, we'll use Taylor-Maclaurin SERIESSUM expansion to approximate the growth, decay, saturation. We begin with the growth, which is equal to R formula, exponent of the x values from -1 to +1. And the decay, which is equal to R formula, exponent minus x. That's for the decay. And the growth, which is equal to R formula, 1 minus exponent negative x. And this is growth. And we'll chart this. Insert chart. We'll use scatter chart. And use row 1 as header and column A as label. We customize our series. All series, the point size will be maximum. And you use trend line to approximate polynomial to the 6th degree. And show the equation as label. And relocate it at the bottom. And we change the color of the saturation to green. Change it to green. And all series, the line thickness will be 1. Next, we continue with the Taylor-Maclaurin SERIESSUM expansion. So it is defined as the summation of a times x to the power n plus k, where the value of n is from 0 to infinity. So 0, 1, 2, up to infinity. We'll get to infinity. This is still good enough for infinity. And the value of n, the value of k will be 0 or 1. So data validation and list of items 0 or 1. That is, if it is decay 0, saturation is 1. And value of n will be -1 or 1. So data validation, list of items, -1 or 1. So the value of m at k equals 0, we'll be comparing the decay and growth. At m equals -1, we'll be comparing decay and saturation. Next, we continue with the formula of the Taylor-Maclaurin SERIESSUM expansion, which is R formula, series sum of the x values raised to the power n plus k. Our n values will be 0, 1 to infinity, while k is 0, 1. So starting is k, and the increment is 1. And the coefficient will be up to this portion, the maximum of our n values. Now we can continue with the coefficients. So this is equal to our formula. We don't have the color for the, so before we continue, we'll revise the chart and change the color of the expansion. It should be black. So that's the expansion. And the point size will be none. The trend line will be polynomial to the 6th degree, the same polynomial. And the line thickness will be maximum. And we'll show the equation as label. Now we have the equation. Now we continue with the coefficient. So our formula, that's m to the power n. So m raised to the power n, which is this value. That's the numerator. Divided by factorial n plus k. So n plus k. So we begin with at k equals 0. So at k equals 0, a value of m negative 1 if it is decay. So it is decay. So our expansion, Taylor-Maclaurin SERIESSUM expansion, is decay, which is this. They have the same values. At m equals 1, then our expansion approximates the exponential growth. So the black one is in red. And their coefficients are the same. So the growth regression coefficients match to the expansion approximately. At k equals 0, so that's k equals 0, at m equals negative 1. So we have a comparison between decay and saturation at m equals negative 1. So our expansion approximates the decay. If k equals 1, our expansion approximates the saturation. So their coefficients are almost the same because this expansion approximates the exponential saturation. Going back to the value of k equals 0, k equals 0, that's the decay. That's the decay, negative 1, m equals negative 1, and it is positive 1, that is for the exponential growth. So exponential growth, where the blue is approximated by the expansion, and m equals negative 1, this expansion approximates the decay. So the black one is on the red datasets. This completes the use of Taylor-Maclaurin series sum to approximate the growth, the decay, and the saturation. All these are exponential growth, exponential decay, and